thing up. All right, so number one, so here what we're just trying to do is fill in this table. So I'll try to do it along with you. So, so Monica, you got the first row. Yeah, good point. So that's that parietal lobe component. I'm thinking let's just keep going and then we'll come back and see if anybody has any. Ariel's actually not here, so and I just realized that after I'd already assigned everybody, so I didn't want to spring it on somebody else. So I guess I'll try to do this one. So this one I had originating out of red nucleus. Is that what you guys put? This is the least important of all of them, at least for people. But it's still very much a lateral column pathway. And it's basically the same as the lateral column, or the lateral corticospinal tract, at least in terms of the movements that it initiates. I don't know if it has the sensory modulation component to it. I'm going to say minimal impact in people or primates. But again, if you work on dogs or something else, it becomes much more important. And I think that's pretty much the story with it. Let's see, vestibulospinal tract. What did you get, Sarah? Yep. I can't figure it out either, and I'm trying to, like, we're really far down for it to be rain. Like that's 2 floors up. So I guess that's just weird air ducts. Okay, yeah, so this is how I spell labyrinth. The labyrinth controls the neck and back muscles. To facilitate balance. I think that's what you said, right? Basically. Yeah, so reflexes that help to control balance when we have something offsets it. That is so weird. It's just really distracting. All right, let's do tectospinal tracts. This one went to Lauren, and she's out too. I know why she's out. She told me she'd be out. That's fine. Yeah, so tectospinal tract. Let's see. So this is coming from tectum. Mostly it's coming from superior colliculus. I think I can say that. I think there might be some axons that come out of the inferior colliculus, but it seems to be reduced in importance. This would be a ventral column pathway. And then, so this is conveying information about visual reflexes that control, or that mostly trigger like neck muscle movements to orient head toward useful stimuli, I'll say. Sound good? Does that sound right? So we're having reflexes. So if you've got some bright flashing thing over on the side of your peripheral vision, that can trigger superior colliculus, which will trigger signals that'll turn your neck. Yeah, I think you're right. And so if it's coming from inferior colliculus, I'll put audio too. So inferior colliculus would be about auditory reflexes, and the superior colliculus is about visual reflexes. So I'll put inferior colliculus too. I would agree with you. Can never remember what the story is in one book versus the other, but I think that's accurate. Anything else on that one? Is that okay? I didn't bring my key with me, so. Yeah. Well, can I do that? I didn't mean to do all of them, but is that better? Is that good? Can you see? Okay. All right, reticulospinal tract. Last one. James, what'd you get?
The pontine part originates in the pons, and then the ciliary part originates in the ciliary.
Yeah. So, not K, T. Yeah, so there's a pontine and there's a medullary reticulospinal tract. I should have had them listed as tracts, but I didn't. Yeah, go ahead.
And then the ventral column.
Yeah, we were talking before we started going. I'll just point out. I mean, I could understand why somebody might put that the medullary one is almost lateral, but it's still, I think, like if you draw the line kind of about right there, like this is all lateral column up here. This is pretty much all ventral column. So I think they're both ventral, despite one being more medial than the other. And then, what was your?
I said the pontine tract maintains standing position, while the medullary tract frees anti-gravity like muscles from ring muscles.
I'll put freeze leg muscles from. So did anybody have any differences on any of these? I kind of did the ones that I talked out, but that seem okay? All right, so you should be comfortable with, basic functions, locations of all these tracks, what they're doing, and that came from lecture as well, but I think it's important stuff. I've heard from like the OT department, for example, that this kind of thing is really critical for them. So it's good stuff to know. I'm going to turn this on so it's a different color. Okay, number 2 says, you're a neurologist, patient presents following symptoms. Inability to wiggle toes on the left foot, perform precise rolls of left ankle when seated and foot is elevated. Nevertheless, they maintain the ability to use their legs and feet during normal walking motions. They don't show any impairment in ability to manipulate fingers in precise ways. You think they've got a lesion in the spinal cord. Your job, though, as the person answering this question is to figure out at what level, in what location, what do you think has happened to this person? So this one went to Fallon. Yep. Did you say what part of Greyhorn? I might have misheard it, but okay. But and then, but because controls motor area, and then in lumbar area, why lumbar? Limb, yeah. I'll put that. Agrees, alternative diagnoses. I guess that's what I'm wondering. Anybody have anything else they put? Alternatives? Yeah, Mary? Oh, you said distal. Yeah. Other ideas? Do you agree, like lumbar-ish area? Didn't say. Other ideas? So to me, the interesting thing about this is, okay, so in terms of location along spinal cord, there's nothing wrong with this person's fingers, right? So whatever the issue is, isn't affecting upper limb, so probably that indicates that we're below the brachial plexus, so we're somewhere in thoracic or lumbar or lower area. So at least that gives us some triangulation. The other hint that or the other clues, I guess, that it's giving us is that they're losing the ability to do precise little things with their toes and their ankle. So these are sort of distal parts of their foot, and they're sort of losing the ability to use those in really discrete or intricate ways. They can't wiggle toes, perform precise rolls. I don't exactly know what that means, but So maybe they're having a hard time rolling their foot in the letters of the alphabet. That's something people tell you to sort of loosen up your ankle. But their legs and feet aren't paralyzed because it says they're still able to use their legs and feet during normal walking motion. So they still have motor output to those areas. They can still, it doesn't say anything about toes, but at least the feet they can still use during normal walking motions. And so because of that, that's telling you that it's not really like a straight up paralysis of that area. It's just sort of loss of fine control in that area. And that's what I'm trying to get at anyway. So I think that makes it more likely that the issue is something to do, something not to do with, I would probably say if you're going to choose an area of gray horn, it would need to be ventral horn, just because that's where your motor area is. But I think probably the fact that they don't have paralysis here indicates that that's actually not where the issue is, because if you had problems with ventral horn or gray matter, that might indicate that that whole area had been damaged, and at that point then you might not have motor output to that area. So you might effectively be paralyzed in that area, have sort of a flaccid paralysis if you lose motor output. Whereas the lateral corticospinal tract is specifically controlling sort of precise distal limb musculature. So I kind of like that answer better. I think it fits the symptomology better. Yeah.
Did you even say that it would be on probably the left?
Yeah, that's a good point. It's yeah. So let's look at the tract. Oops. Wrong way. Yeah. So the decussation if it is lateral corticospinal tract, like you said, it decussates in the medulla, so it's traveling down ipsilaterally and then innervating that side of the body. So that would indicate that if the damage is on the left side, was that what it was? Yeah, so if the problem is on the left side, not the right side, that would indicate that probably it is left side of spinal cord. And I would probably agree lateral corticospinal tract. So I'm gonna put a line through that one. I hate doing that. It feels so rude. But I think the fit is better for lateral corticospinal tract. And agree left. Yeah. Yes, it would be white matter then. Okay. Sound good? So you can have precise little lesions. Usually probably not from like traumatic spinal cord injury. I guess it's possible from that, but if there's some kind of a local, disruption or inflammation that occurs in that area, it can lead to these kinds of deficits. All right, let's keep going. So number 3, this is my Olympic skier question. So what we need to do is for each of these scenarios, identify which of the areas, premotor area, supplementary motor area, primary motor cortex, which would be expected to be active in those spots. For B, I did have one where I just kind of said you probably don't know, because I don't know either. But at least for A, so 3A, this one went to Katie. What'd you get? I'll try to highlight. Yes for preem and no for here. And what did you put for explanation? Agrees, disagrees? Get no responses. I'll move on. What about this one? So this went to, who did it go to? Bailey. You said no? Oh, M1 is not. Yeah, so the SMA one, I agree. You can't really, well, I agree that's a reasonable expectation for it, I guess is what I would say. So it's really hard to know. I guess it sort of depends. Is the skier at that moment like actively planning some kind of motor action, or are they more just anticipating based on an external signal? But I think it's reasonable to assume SMA is probably active, but I don't think we can know for sure. But I like the, so for PMA, the best example we had for PMA is that case of the monkey looking at the warning light versus the trigger light thing. And so its PMA would turn on when there was a signal saying it's almost time to move. So you're like anticipating that action. So PMA, I think this would be a prime example where PMA would be expected to be active, because you have an external stimulus that's allowing you to anticipate that you're about to start moving. But also, you haven't started moving yet, so if you're not moving yet, then M1 should be silent still. Yep?
With the M1, does that include, like, if she's tensing up, like, getting ready to jump off, would that still, like...
Yeah.
I'm asking, does that
No,
count?
I think it would, yeah. Yeah, so if you're like, kind of getting, you're getting prepped, you're moving at that point. You're exercising or using your muscles, and so, yeah, that probably would trigger M1. I was imagining that they were not, to make it easy. But yes, that's very reasonable. Yeah. So yeah, I think you're right. So I think if we are going to be pretty simple-headed about it, and that probably is pretty simple-headed, but this is how it's pitched in your book, and it's how I'm pitching it, that the PMA's job is to respond to external stimuli. If we argue that there's no external stimulus in part A, then I think we could probably argue that maybe there's no activity in the PMA area here, because this is the idea of the person just sort of closing their eyes, just imagining themselves being moving down the slope, but they're not actually doing anything. They're not really seeing anything. There's nothing really external that would trigger that. And so under those circumstances, you might actually expect the PMA not to be active. So I actually would have probably put not. It kind of depends on what exactly is going on there, if there is some kind of a stimulus. But I think as described there, they're just mentally rehearsing. They're not getting signals. It does say not yet moving and receiving no signals that they're about to be called on to ski. So to me, I would probably lean PMA off at that point.
Would you say if her eyes were open that there would be external stimulus just from like a visual perspective with seeing it in front of her and seeing the
Well,
people around her next to her?
Ways to the top of the hill.
Does that kind of depend on like more of a
Yeah, I mean,
space versus open?
I
I
guess.
feel like that would definitely
Yeah, so it does say that she's standing there
I just didn't
at
know
the top of the
if
hill.
her eyes were closed or not.
It
So
doesn't.
If her eyes were closed, then that would make sense. But if they were open.
But it does say receiving no signals that she's about. So like,
Yeah, I put no too. I was just
Yeah.
thinking like if her
But
eyes
yes,
were
if she's standing perched there at the top, looking down this hill, that alone could be a signal that she's about to fire. So at that point, then we could argue PMA active.
That's so cool.
All right. And I'll say, like, the purpose of this is to just make us think about what each thing does, not so much to. There's ways in which you can argue each of these. I would agree. Let's do C. So where is that? Leandra, what'd you get?
PMA, yes, but only at the beginning of the movement.
Okay.
SMA, no.
Okay. Okay, and so, and you said PMA only at start. Why? What-
Stops firing after it's done starting the movement and after the anticipation.
And then what about the other guys?
The SMA is no longer planning the movement, so it's not active.
And then M1?
It's always firing during the
Yeah, so here we're finally moving, right? So I feel like M1 is the most straightforward of all these. If you're not moving, M1 should be silent, and that includes like not tensing up and that kind of thing. In C, they're clearly moving, they're flying down the hill, and so at that point, M1 is going to be going crazy. PMA, I'd agree. So we're sort of responding to a stimulus. The PMA will tend to, if the stimulus is restricted at least to the little start lights and sounds, then at that point, then PMA might shut off slightly after you start the action. Although I guess you could argue as you're hurling down the slope, there's constant bombardment of new stimuli, so I don't know. Those new stimuli might trigger it to start working. SMA, I don't know. I think you could make an argument either way. I mean, the one thing that we did see in that chapter when we talked about SMA here is that SMA was active during the complicated finger wag sequence. It never really told us that it shut off. So I think you could reasonably make an argument that SMA, unless it somehow ceases to need to generate new motor plans, you could argue maybe it's still going. But
Would you say that like the movement of a skier, like just standing there holding, like leaning from side to side, that's not really that complex in a sense. You're not using like fine motor skills.
yeah, yeah. Gripping versus, I guess I'm imagining this person like flying down a hill doing slalom or something, and they're like doing all kinds of stuff. I mean, I don't know. It seems pretty complex to me, but I can't do it. Like I just fall. So I just.
Because the person who is the Olympics, it's not like they can practice all the time with the same exact path every second.
Yeah.
Become routine movements.
Yeah. I think it's getting to be a pretty darn complicated movement compared to just gripping something like that. I think it's more. So I don't know. I kind of lean yes for all these guys, to be honest with you. SMA again, because I don't think we had indications that it does turn off during complicated pattern generation, like what we did see with PMA. And I think with both of those two, you are going to be constantly bombarded with the need to readjust and modify what you're doing throughout the entire descent. So I kind of lean yes for all of them. But I understand the argument. So again, my purpose in putting those on there, it's not so much maybe to get to like an absolute yes or no, but it's more to like to puzzle it out and think about like what each of those different regions is responsible for doing. So like what kinds of things is M1 supposed to do, and what kinds of things is SMA supposed to do and PMA supposed to do. The major distinction I always think of for PMA and SMA is PMA, we really focused on it being responsive to external stimuli, whereas SMA can be responsive to internal stimuli, where you're just sort of mentally rehearsing or executing some sort of complex motor action. All right, let's do 4. So 4 is looking at Parkinson's versus Ballism. And this one's kind of cool because it's directly relating to this motor loop issue or process that we talked about. So shucks. So Colton's also gone. So well, let's just do this. So, I could do this without going to a picture, I mean. What are symptoms of 2 diseases? So Parkinson's, I guess I'm going to give you 2 major ones. So one thing with Parkinson's is you have a resting tremor. So when you are at rest, not actively trying to use your muscles in some sort of way, people that have Parkinson's just tremor like crazy, and we saw that in the video that comes up next. You also have this difficulty in initiating action, I would put. So it becomes more difficult to start. Once you start, you're kind of okay, but that starting of the action can sometimes be a very difficult thing to do when you have Parkinson's. Ballism, there's just sort of like these large, I should say, large involuntary ballistic movements. of limbs. So ballistic, like a ballistic missile is kind of arcing up through the air, and that's what you see people doing with that have it. They're just kind of, and it's involuntary. I mean, it's just got to be really irritating, beyond, to say the least, and disabling because you're losing motor control and you're doing these sort of spontaneous, ridiculous actions that destabilize you. That's what I put. Do you guys agree? Yeah. I don't think I can explain that one. I also can't really explain the resting tremor, based on the motor loop at least. So yeah, I don't know. So it's the next bit though, at least we can explain one of those things, and that's the difficulty in initiating action. So why is it that the loss of the specific brain area cited above, oops, I was supposed to answer that part. So loss of, where does it say to do that? That's a terribly written question. God, what an idiot. Oh, no, it says it. It says it in the question. All right, good. Not totally bad. That's not so bad. So, okay, so Parkinson's was loss of substantia nigra. Ballism is loss of the subthalamic nuclei. So why would losing that brain area lead to some of the symptoms? So this one went to 4B. Where did it go? That one went to Maria. What'd you get? So therefore, that explains the loss of ability to initiate an action if you're losing the dopamine by your argument. Okay. What did you get for ballism? So if you don't have it, you may have these involuntary movements. Voluntary. Any additions or differences or anything that you'd like to add to these? So just to add a little detail, so substantia nigra is here, right? So it makes dopamine. So dopamine then triggers, and doesn't trigger, you could say it potentiates the putamen neurons, so you can sort of think of dopamine as like constantly being released. But then that facilitates the ability of frontal cortex neurons to trigger this loop, which ultimately leads to actions starting. So if you lose the ability to make this neuron get excited because you don't have enough dopamine anymore, that means the frontal cortex neurons will have a harder time getting these guys going, which means this whole loop has a harder time running, and therefore you have a harder time triggering and initiating movements. Because the whole point of this loop is to initiate an action, initiate movements. So if you can't do that, it becomes really hard to make movements happen, and that's because that's happening because you're losing that excitation caused by dopamine from the substantia nigra on the putamen neurons. So that's that one. So I agree with what you. I would like to add a little more. So dopamine. Oops. So what I said is dopamine facilitates the motor loop by stimulating the putamen neurons, which ultimately results in initiation of the muscle movements. So again, the argument is if you don't have dopamine, because you don't have your substantia nigra neurons anymore, they're all dying, that's going to result in it being very difficult to get signals to go through this motor loop. Still can happen. You can still do it most of the time, but it's more difficult to do so. And this also explains why one of the major treatments for Parkinson's is you basically give somebody a dopamine precursor called L-DOPA, and that increases the amount of dopamine that is going to be present throughout the brain, but at least throughout in that particular key area, so you can initiate an action. Subthalamic nuclei are here. So that's this neuron in this little schematic. So if you look and see what this job of this neuron is supposed to cause this neuron from the globus pallidus to become excited. If it gets excited, so that's an excitatory synapse, if it gets excited, it will inhibit neurons in the thalamus, and then the thalamus neurons in turn will not be able to send signals up to the supplementary motor area. So this thing is in charge basically of preventing unwanted movements, because as long as this thing's active, that keeps your thalamus neurons inhibited, which in turn prevents them from firing. And we have to overcome that inhibition by shutting down this neuron when we initiate the motor loop. But again, like the job of the subthalamus neuron is basically by working through your globus pallidus neurons and the thalamic neurons, we're preventing the thalamic neurons from firing when we're not wanting to. So if you then lose these neurons, so if they go away, now this neuron never has a reason to get excited. So if it's never excited, the globus pallidus neurons, they're never going to send inhibition to the thalamus, which means the thalamus is never inhibited. So the thalamus can just fire whenever the heck it wants at this point. So it's just, the result is you get these unwanted, ballistic, aggressive, frustrating movements that occur with ballism. So I'm going to just type it out a little more. So basically, if you lose subthalamic Uh-oh. Okay, so I wrote, if you lose the subthalamic neurons, you lose the ability to inhibit the thalamus neurons, these guys, via the globus pallidus neurons. If you stop inhibiting the thalamus neurons, the thalamus can now fire spontaneously, which will result in you having these sort of involuntary actions. Does that make sense? Getting some nods. Good. Yeah, I think it's kind of cool. And so it does explain what's going on with these poor people that have that particular problem. This last bit, I think, is just kind of cool. I always thought this was an interesting little story. This also went to somebody who's not here. We have attendance issues. I'm sorry. I was looking at 5C. I was looking for Amanda, but I know she's out of competition. Yeah. So what'd you get, Olivia? And just sort of add so less something that. Yeah, it's not super obvious to me what's going on here, but there's something about the music that as they start to move with the music, I just sort of imagine maybe their whole bodies are just sort of, they're starting to get some sort of subtle movements going on. And once that happens, then that may facilitate future movements because their muscles are already active. They may not have to run signals exclusively through this motor loop in order to get actions to occur. You're sort of, you're kind of priming the body here somehow through this process. And I think it's a really neat phenomenon. It'd be great to know a little bit more mechanistically about exactly what's going on here, but it does seem to work for people. I think that's a really cool little story. Bless you. All right, so we are out of time. So we will have to do 5 and 6 when we come back. So thank you very much. I'll see you guys on Monday. I totally thought we were in question 5 somehow. So.